Hello. In the last unit of this course, we will spend some time talking about electric current. Well, it is very different from the astronomy, geology, and meteorology that we have been discussing so far. In order to discuss electric current, we need to talk about electric charge. What are electric charges? Where do you find them? Well, electricity is fundamental to nature. Everything in nature is made of electric charges. Now you know that all of us, everything around us is made up of atoms. Atoms, which are the basic constituents of matter, are made up of electrically charged particles. There are two basic types of charges. What are they? Positive charge and negative charge. Now, an atom is made up of protons, which are found in the core of the atom. Now, protons carry a positive charge, and then the charge carried by the proton is written as small e. And the protons are fixed to their relative positions. So an atom contains proton at its center, and they carry a positive charge which is represented by E. Now here I have the picture of an atom. Now the blue balls are the protons and the red ones are called neutrons. They don't carry any electrical charge. And there are electrons. They carry a negative charge. So if a proton carries a charge E, then the electron carries a charge negative E. That means if you put a proton and an electron together, they will cancel each other. The net charge will be zero. So in an atom like this, where there are two protons and two electrons, the atom as a whole is an electrically neutral object because there is equal quantities of positive and negative charges. So that's a proton, and these are electrons. Electrons are found moving in the space surrounding the core of the atom, and they carry an equal amount of negative electric charge, negative E. There you are. Alright, now this is the picture of an atom. You got a positive core, and around the positive core you have negatively charged electrons moving around, and that tells you that the atom as a whole is a neutral object. Now, if you can take one of these electrons away from the atom, then the atom becomes electrically charged. It will then have more positive charge than negative charge. Well, we will talk about that as we move on. Now, E is the fundamental unit of charge. That means every other charge comes in multiples of this. Now, this means that the charge carried by anything else comes in multiples of this E. A proton and an electron together form a neutral object with no net electric charge. Now, the rod I am carrying now is electrically neutral because it contains equal amounts of positive and negative charges. Everything I have around here are neutral because they contain equal amounts of positive and negative charges. So this means that a neutral object contains equal quantities of positive and negative charges. All of us are made of electric charges, equal quantities of positive and negative charges. If I lose some negative charges, you see, I can actually lose some charge by rubbing something onto my hair. If I rub something onto my hair, it gets electrically charged by looking at this. You know, if I bring it, if I rub it to my hair, well, I don't see anything happening. Well, maybe I'm not losing any negative charges. Well, we will see that as we go on. Electric charge is measured in a unit called coulomb, represented by the uppercase C. Now, this is a large unit and it is divided into, you know these notations, millicoulomb. A millicoulomb is 1,000th of a coulomb. Microcoulomb, a millionth of a coulomb. Nanocoulomb, a billionth of a coulomb, and so on. So a coulomb is actually a very large quantity of charge. The value of the fundamental unit of charge is E equal to 1.602 times 10 to the power of negative 19 coulombs. It's a very small value. You need a very large amount of electrons, a very large number of electrons to make up 1 coulomb of charge. Let's now talk about conductors and insulators. If you look around, we see different materials. Some of them will allow electric charges to flow through them, electric current to flow through them. Some others won't. So we got materials that can be classified as conductors and insulators. While protons are fixed to their relative positions in a material, electrons are free to move. Electrons move around the atom. Now, in some materials, especially metals, you know that metals are good conductors of electricity and heat. Now, the reason is this. Electrons that are relatively at large distances from the center of the atom normally wander about. They do not really belong to a particular atom. They wander about within the materials. They are loosely bound to the atom and they are virtually free to move about in the material. That is the characteristic of a metal like this, which is a good conductor. Now let me show you an animation to explain what a good conductor is. Now this is what happens in a conductor. You see, this is the atoms of a material like this, and there is the central nucleus and the electrons moving around it. And the electrons that belong to the outer layers, they do not have a lot of affinity to this atom. They can move about. Now look at the way those electrons really do not belong to any particular atom. They keep wandering about. So these are called free charges. So a metal like this contains free electric charges. They can be made to move from one end of the conductor to the other. It is called a good conductor. Whereas in a material like this, a pen, this is a bad conductor or an insulator where there are no such free electrons. Alright, let's move on and talk more about electric charges. Now, if there is some excess charge on this conductor, if I place some excess charge on this conductor, that excess charge will move along the conductor, will move over the material because it allows charges to move through it. And such materials are called conductors, good conductors of electricity or electric charges. Now, most metals are considered to be good conductors because all metals have these characteristics. In some other materials, electrons are completely localized and are not allowed to move from one atom to another, and they cannot therefore move from one part of the material to the other, and therefore they are insulators or bad conductors. So you must be able to distinguish between conductors and insulators. Now, both conductors and insulators play vital roles in building electrical circuits. You see, we are able to build electrical circuits at home because we have good conductors. We use copper for taking electricity from one place to the other. And we have good insulators. Most of the materials used in building houses are bad conductors. You see, imagine if all materials were good conductors, we would not have been able to use electricity at home because we will get electrocuted all the time. Now, interaction between electric charges. How do a positive charge and a negative charge interact? Now, the fundamental properties of electric charges are opposite charges attract. If I keep a positive charge and a negative charge, they will attract. A negative charge and a negative charge will repel. So like charges repel. Two positive charges placed together will move away from each other. Similarly, two negative charges will move away from each other. But a positive charge and a negative charge will move towards each other. Now here I have the illustration. A negative charge and a positive charge, they like each other, they attract each other. Whereas a negative and a negative repel, a positive and a positive also will repel. Now an electroscope like the one shown below can be used to detect the presence of an electric charge. Now here is an electroscope. Now an electroscope has a conducting platform, a conducting stem and conducting leaves. Now what happens is, when you place some excess charge on the platform, because it is a good conductor, the stem also is a good conductor, those excess charges will move, and when they come to the leaves, both the leaves will have the same type of charge, they will move away. Now let me see if I can show an electroscope to you. Well, it may work, it may not work, but I will try. Now, let me first of all show you a demonstration how I can actually charge an object like this. If I rub this, I have a piece of wool in my hand, W-O-O-L, wool. And I'm going to rub this plastic sheet with wool. Now, what happens is, when you rub, some electron from this wool is going to transfer onto the plastic. That means the plastic will get some excess charge. I hope it does. Let's see if it is going to work. And I have a very light ball suspended here, and I'm going to bring this charged object near it. See what happens? Watch what happens. Look at that. You see? Well, why is this now going away? If you notice, this is what I'm holding is a negative charge, and when it came and touched, well, you can see it came and touched, it obtained some negative charge, and now the negative charge and the negative charge are repelling. You see, when I take it, goes away. Let me see if I can. No, it doesn't let me touch it. There you are. And now it touched, it got the same kind of charge. There you are. Well, you can play with it actually to study the interaction between charges. Okay, now let me show you an electroscope. An electroscope, I have a small model here, and it looks like this. Let's see if I can show this to you. Now, an electroscope, that is my model. This is the platform that is conducting, that is the stem, it goes down, and those are the leaves. Now, if I can place some excess charge here, those excess charge will move down, and both the leaves will get the same type of charge. that will make them move away. You think it will be possible? Well, I'll try. I can't guarantee. What I'm going to do is I'm going to charge my plastic by rubbing it as hard as I can, hoping that it will get some electrons transferred from the wall to the plastic. And if that is the case, I'm going to bring it towards the electroscope and see what happens. Now, I want you to watch it. Even before touching it, why is the leaves moving? Anybody tell me why is the leaves moving? I haven't touched it. You see, this now has some excess negative charge. When that excess negative charge comes close to the electroscope, the negative charges on this don't like this negative charge. They just move away to the leaves. That's why the leaves now diverge. You see that? Alright. Now, I want you to watch this. This process is called polarization. That means the charges in this electroscope are polarized, means split. This is negatively charged. When it is brought near the electroscope, the negative charges on the platform do not like the presence of this, so they move down to the leaves. And that's the reason why the leaves now diverge. Alright, watch when I touch the electroscope. Look at that. The leaves really diverged. Alright. Now, watch what happens when I touch the electroscope. When I touch it, those excess charges are going to flow through my body. See, now the leaves have collapsed. Alright? So an electroscope is a good way to study electric charges. Alright, let's look more at the electroscope. Alright? So that is the electroscope that we were looking at, which is very similar to the one I just showed you. Now, it consists of a conducting platform connected to a conducting stem that carries a light conducting leaf. The stem and leaves are enclosed in a glass case. If some excess charge is placed on the platform, it spreads onto the stem and the leaves as they are conducting, and therefore as the leaves and the stem acquire. I want you to watch this. If you place an excess charge, you can see the leaves diverge, and when you touch, what happens? The charges move to the earth through your body. So as the leaves and the stem gets the same amount of charge, they move away. And when you touch it, the leaves will collapse. Watch it one more time. When you place an excess charge on the platform, it spreads through the leaves and the leaves will diverge. Alright. And when you, now here, this is positively charged. This is negatively charged and this is positively charged. Now when you touch a positively charged electroscope, what happens? Negative charges from the earth will come in and neutralize those positive charges, because motion is allowed only for the negative charges, not the positive charges. Alright. The extent of divergence of the leaves is proportional to the amount of charge placed on the platform. You place more amount of charge, the divergence will be greater. Now, how do you charge an object either positively or negatively? Generally, all objects are neutral, which means that they contain equal amounts of positive and negative charges. You see, I showed you how I charged this plastic rod by rubbing onto this. Now, normally this is neutral and this also is neutral, which means that each of these contains equal amounts of positive and negative charges. Now, so this is a neutral object. It contains as many positive charges as there are negative charges. Now, if some negative charges are removed from an object, if you can remove some negative charges from here, then this object will have some excess positive charge. We will call that object a positively charged object. And this is how I'm going to represent a positively charged object. You see, a positively charged object is an object that contains an excess amount of positive charges. Similarly, if some negative charges are added to the object, it will have some excess amount of negative charge, and we will call that object then negatively charged. Now here I have a negatively charged object. When one object is rubbed with another object, as I just showed you, electrons from one object could migrate to other objects, leaving the first one with a net positive charge. So look at this. When I rub this plastic sheet with the piece of wool, what happened? The plastic sheet took away some electrons from the piece of wool. So the piece of wool has a net positive charge, and the plastic now has a net negative charge. When a plastic rod is rubbed with fur, well, I used a piece of wool. Fur is actually better. It is observed that some electrons move from fur to the plastic, making plastic negative and wool positive. Now this is made possible by electrons getting transferred from the fur to the plastic. Similarly, if a glass rod is rubbed with silk, what happens is the glass rod acquires positive charge. In other words, electrons from silk will transfer to the glass rod. So the transfer of electrons depends on the nature of materials. So here I have a positively charged perspex. That means this is now missing some electrons. Now this is because electrons move from glass to the silk, giving silk an excess of negative charge. Thus, a positively charged object has some excess positive charge, and a negatively charged object has some excess negative charge. That is the meaning of a charged object. Now the earth is a large reservoir of charges. You can either dump charges to the earth or pick charges from it. In other words, if I have a positively charged object, if you connect it to the earth, negative charges from the earth will come and neutralize those positive charges. On the other hand, if I have a negatively charged object and connect it to the earth, the negative charges will flow to the earth. The net result of connecting anything to the ground is that it will get neutralized. So, if you touch a charged object, the excess charge on the object flows to the earth through your body, as the human body is a good conductor of electric charges, and the object becomes neutral. Let me see if I can show that to you again. You see, these things don't work all the time, but we can try. Well, let's see whether you can actually see this. Now, I'm going to rub the plastic with the piece of wool and see if I can charge this. What kind of charge is the plastic going to get? Negative charges. And if I'm lucky enough to get it charged, if I touch the electroscope, well, you can see it got some charge. If I touch that, well, the charges have flown through my hand to the earth, neutralizing the electroscope. Well, that is the process of grounding or earthing. Alright, so this process is called grounding. Now, here I have shown you how to charge a neutral object by conduction. Now, conduction means you allow charges from one object to flow into another by making contact. Now, you're going to charge, this is the electroscope. Now, I'm going to bring a negatively charged object and make it in contact with the electroscope. What happens? Some of these excess charges from the charged object will flow into the electroscope, just like I showed you now. And the electroscope now has some excess charge. Now, this way of charging the electroscope is called charging by conduction. You see, conduction means by actual contact. When you make a charged object in contact with a neutral object, the electroscope is actually neutral. So when you bring a charged object and make it in contact with the neutral object, the negative charges will flow into the neutral object. Now when you remove the charged object, some of the charges are now on the electroscope, on the neutral object. This is now electrically charged. But remember, the total amount of charge has to remain a constant. That means if you now add up the charges on the original object and the electroscope, it will be the same as the original amount. Okay, the total charge in the two object system will remain a constant. Some charges from the charged object moved into the neutral object, making it charged. Now, here I have shown how to charge a neutral object by using a positively charged object. Now watch what happens. When a positively charged object is brought in contact with this neutral conductor, this is a neutral conductor which has equal amounts of positive and negative charges. What happens? Some negative charges from the neutral object move to the charged object. So each time an electron from here moves here, that positive charge will get neutralized. So each time an electron moves away from here, a positive charge is created. You see, when you miss an electron, an excess positive charge exists. So the result is the neutral object gets positively charged. So this is the process of charging by conduction. So when you charge an object by conduction, what do? You bring a charged object. Now here, I'm going to show that one more time, although my experiment may not work well. When I want to charge the electroscope, here I have the electroscope, by conduction, what I need to do is I charge an object. Well, I try my best to charge it. Don't tell me I'm not trying. Alright? I will rub as hard as I can. Now, and bring the charged object and make contact. Well, I didn't succeed because, well, let me try another one. Well, let me try another one. Because these objects get hot very fast and they become very ineffective. So, if I try it again, I hope it will work. Now, there you are. I made it in contact with the electroscope and charges, they shared charges. This is charging by conduction. And now, when it is charged, if I want to discharge it, all I need to do is go and touch it. And the charges are gone. Alright. Let's now move on. You just move it away. Okay. Now what is electrostatic induction? Now do you remember in the beginning when I brought the charge close to the electroscope without touching it, the leads showed divergence. And I told you why it happened. Because charges inside the neutral conductor split. I used the word polarization. And that is what is called induction. Induction occurs not by real contact, but by the presence, by bringing it closer. when a negatively charged object is brought near a neutral conductor, the negative charges in the neutral conductor will move away from near the charged conductor to the other end. In other words, let me see if I can show that one more time. I'm not confident it will work, but I will try and see what happens. Alright, I will try and charge an object by rubbing it, and this time I am not going to touch the platform of the electroscope. I'm only going to bring it close to the electroscope. Now, if you remember what happened in the first time, even if this doesn't work, you know what you saw. Now look at this. I haven't touched the platform, but the leaves are diverging. Why are they diverging? Because the mere presence of these negatively charged objects have driven a lot of negative charges from the top to the bottom to the leaves. So the leaves have now diverged. Now this process is called polarization. Now when a negatively charged object is brought near a neutral conductor, the negative charges in the neutral conductor will move away from that end towards the leaves. Now that process is what we call polarization. Now this splitting of charges in the neutral conductor due to the presence of a charged conductor near it is called polarization. Now if the neutral conductor is now grounded, what will happen is those negative charges will actually go to the ground, leaving the neutral conductor positively charged. Now, if now the grounding is removed and the charged object is taken away, the original neutral object will be positively charged. Now, I don't know whether I can show that to you, but I can try. Well, let me try one more time, see how this will work. All right. I'm going to rub and charge it as best as I can. Okay. Now what happens when I bring it close to the electroscope? Well, the leaves diverge, is that right? Well, now the leaves diverge due to polarization. Now you can see this is polarization. Now in the next step, if I ground the electroscope, I touch, what happens is I am providing the path for those negative charges to go to the earth. Now I remove the earthing and remove the charged object. Did you see the electroscope has now shown a divergence? Now what is the excess charge on the electroscope now? The excess charge is now opposite to this, positive charge. Now I can test it. Now tell me, the electroscope now has positive charge. If I bring the negative charge towards the electroscope, would you expect the leaves to converge or diverge? Because when you bring the negative charge close to the electroscope, it will drive away negative charges from the top to the bottom. And the leaves now has positive charges. Therefore, you would expect the leaves to collapse. See what happens. You see that? The leaves are now collapsing. Can you see it? It's actually happening. That shows that the electroscope now actually carries positive charge. Now, this way of charging is called charging by induction. Charging by induction. Well, I want you to now do a small lab. Remember, our labs are designed to reinforce and understand these concepts. So let's now do a small lab where I would like you to write down some of these things. Alright, the first thing to do is, alright, get your worksheet. On the worksheet, I have given you these questions and the space to write. And once you complete the worksheet, now you can complete it on the computer, save it as a Word document and email it to me. So write down what a charged object is from our discussion so far. If you want a repeat of this, you got to go back and listen to me again. So write down what a charged object is. How will you charge a neutral electroscope? By conduction. I showed you in the diagram and also in the lecture here how charging can be done by conduction. Well, when a charged object is brought near a neutral electroscope, its leaves diverges. See, I just showed it to you. When a charged object is brought near a neutral electroscope, you saw the leaves diverge. Explain why this happens. I want you to put it in writing in your own words. Alright? When a charged object is brought near a neutral conductor, polarization of charges occurs in the neutral conductor. Now, tell me what you understand by the term polarization. So answer these 4 questions. And now I'm going to give you a scenario. And that is, watch the animation on the next slide. Watch it very carefully. This is a lab, so you've got to observe. Watch the animation on the next slide and explain how to charge a neutral conductor by induction. I just showed you on the electroscope how to charge by induction. Now I'm going to show you an animation of the same process. You need to explain the process. Alright, watch this. A charged object is brought near, polarization occurs, negative charges moves away to this end. And now ground that end, the negative charges are all gone. Remove the grounding and now remove the charged object. Is that right? Now this object retains a net positive charge. Now this is charging an object by induction. Again, bring a negatively charged object close to the neutral conductor. What happens? Polarization happens. Now the neutral conductor is grounded to take away those negative charges as far away to the earth. Now leaving some excess positive charge on this conductor. Remove that charged conductor, the object retains positive charge. Is that right? I want you to write this in your own words, although they are actually written down here, the explanations. Alright, watch the animation a number of times and see what happens and write down an explanation of charging a neutral object by induction. Write it down on your own. Alright, I want you to watch now this. Watch this animation and explain in your own words what actually happens. Now I want you to watch it from the beginning. Alright, how does it start? Now forget about this, let's look at the start first. In the beginning there are 2 neutral conductors, they are both neutral. A charged object is brought near, what happens? The negative charges went all the way to here. And now remove one conductor. What happens? This will have some excess negative charge and that will have some excess positive charge. Interesting, isn't it? Well, very fascinating actually, electricity. Watch one more time. Bring a negatively charged object near. Don't touch it. That negative charges drive all the negative charges to the farthest point here. And now remove that second object. That means these negative charges cannot come back. So this has some excess negative charge and that has some excess positive charge. So watch this animation and explain in your own words how the 2 neutral conductor became charged. Alright, complete this lab again and email it to me. Okay, now let's look at another important concept in the electric charges, Coulomb's law. Okay, now what does Coulomb's law say? Coulomb's law gives a quantitative description of the force between 2-point charges. If you have 2-point charges placed at a distance, suppose I have 2-point charges here. This is one charge, this is one charge, this is another charge, placed at a distance r from each other. Coulomb's law gives us a way of understanding or measuring the force between the two charges. Well, let's see what that is. It says, the Coulomb's law says the force between 2-point charges varies directly as the product of the two charges and inversely as the square of the distance between their centers. I don't think you need to overtly concerned by it. Now, I can write this as an equation. Those who know a little algebra, it tells you the force between the two charges equal to a constant k times q1, q2 divided by r squared, where q1 is the charge on one object, q2 is the charge on the other object, and r is the distance between them. K is a constant, and that has a value which always has this value, 9 times 10 to the 9, and don't worry about the units as far as you are concerned. Now, force is measured in a unit called Newton. So, the force between the electric charge is measured in a unit called Newton. So, a negative charge and a negative charge will repel with that force. What is the force? F equal to K times Q1 multiplied by Q2 divided by square of the distance between them. Whereas the force between a positive charge and a negative charge is an attractive force. Let's do a small problem. Why not? Do a practice problem. An electron and a proton each carries a charge. You see, I gave you the fundamental unit of charge. E is 1.6 times 10 to the negative 19 coulomb. If in an atom, the distance between the electron and the proton is 1.2 times 10 to the negative 10 meter, what is the electric force between them? Well, all we need to do is go and pick up that formula, F equal to K Q1 Q2 over R squared. Alright, try and practice it. You know the value of K, I gave it to you. Q1 is this. Q2 also is that, because an electron and proton both has the same amount of charge. One is positive, the other is negative. And the distance between them is this. Let's put all those values in there. This is the value of K. This is the value of Q1. And this is the value of Q2. And this is the value that they are separated, the distance between them. And if you know how to put this on a calculator, you can actually solve it by putting it on a calculator. Right? Well, I have given you the various steps. See whether you can follow that step. And that will give you a value like 1.6 times 10 to the negative 8 Newton. Well, I just showed you an example of how Coulomb's law can be used to calculate the amount of force between charges. Well, you don't need to really worry about calculations of this type. Okay? Let's move on. Let's now talk about another concept called electric field. Now, what is the meaning of a field? A field is actually a region. An electric field, suppose this is an electric charge. This is the electric charge. This electric charge has an electric field. Now, what is the electric field of this charge? It's a region around this charge where it will exert force on other charges. That is the definition of electric field. So force between objects, whether electric, magnetic or gravitational, can be explained using the concept of a force field. A force field is a region, is a space where the object will experience a force. You see, this object, if I drop it, it falls. You know why? Because that object is placed in the Earth's gravitational field. Any force can be explained by using the concept of field. Now, we are all in the gravitational field. If I jump up, I'm brought back because I'm in the gravitational field. You see, a space around the Earth where the Earth exerts force on objects is called the gravitational field of the Earth. In the same way, if I have an electric charge like this is an electric charge placed at a point. There's a space around it where you place another electric charge. This is another electric charge. All right. So I'm placing this electric charge in here. This will experience a force. Now, if this is a positive charge and this is a negative charge, this will go and towards it. If this is a positive charge and this is a positive charge, this will move away. You see that? Why? Because this is placed in the electric field of this charge. So that is the meaning of the electric field. So electric field is a three-dimensional space around an electrically charged object where it will exert electrical force on other charges. So if you want to talk about the electric field of a charge like this, the electric field of a charge like this is a three-dimensional space where it will exert force on other charges placed in that region. A positive charge attracts a negative charge because the negative charge is in the field of the positive charge. Look at this. I have a positive charge here. That means anywhere around it you place another charge, this will exert a force on it. Why? Because the field, the space around it is its field. So if I place a negative charge here now, this negative charge experiences a force. Why does it experience a force? Because this negative charge is now placed in the field of that positive charge. In the same way, if a positive charge is placed in the space around a positive charge, now this is a positive charge. If I place a positive charge here, this will experience a force. That way, it will be a repulsive force. Why? Because this positive charge is placed in the electric field of this charge. Alright, I hope you got a concept of electric field. Now, electric field at a point in space near a charged object has a magnitude and a direction. So electric field has a value and the field has a direction. You can see this field is directed away from the positive charge, right? So a positively charged object will repel a positively charged object. An electric field has a direction and a value. Now, to define an electric field, we use a standard test charge. You see, in order to define an electric charge, we use a standard test charge. And a standard test charge is a unit positive charge. Alright? So, a standard test charge is a unit positive charge. So, we will we will define an electric field based on the behavior of this unit test charge when it is placed in a given space. Is it going to go this way or that way? How much is the force it experiences will tell you or give you information about the electric field. So if a positive test charge is placed near a positively charged object. Now tell me, now here is the positive test charge. This is a small positive charge. And here is a positively charged object. Now tell me, if I place it, this is a positively charged object, the maroon one, and this is the positive test charge. Tell me, which direction is it going to go? Is it going to move towards the charge or away from the charge? Well, light charges repel. So this unit test charge, which is a positive charge, is going to go away from the positive charge. You see that? So if a positive test charge is placed near a positively charged object, it will experience a repulsive force and move away. Now here is a positively charged object, and here is the positive test charge. Now this test charge is going to move away. Now the direction of motion of the test charge is the direction of the electric field. Alright? Now similarly, if a positive test charge is placed near a negatively charged object, what will happen? Now here I have a negatively charged object. If I place my positive test charge here, what will happen to that test charge? It will be attracted. There you are. That means the field, electric field now is in that direction. So, watch again, the direction of an electric field is the direction in which a test charge will move. And a test charge is a positive charge. So, a test charge will move away from a positive charge and towards a negative charge. That means the electric field of a positive charge is all directed away from it. Similarly, electric field lines of a negative charge are directed towards it. The path taken by a test charge placed in an electric field is called a field line. A field line. If I now trace the path of this positive charge, which will be that line, this is called a field line. Now tell me, the field lines of a positively charged object, will the field lines be directed away from it or directed towards it? Well, the field line is the path taken by a unit positive test charge. A test charge, a positive test charge, will move away from a positive charge and towards a negative charge. That means the electric field lines will all originate or diverge from a positive charge and all converge to a negative charge. Alright? So electric field around an electric charge can be mapped by drawing these field lines. I'm going to show you how this can be done. Look at the electric field lines of a negatively charged object. What it tells you is, if I keep a unit test charge here, it will move in this direction. If I keep a unit test charge here, it will move that way. This is a field line. Each of these is a field line. Similarly, this is a positively charged object. If I keep a unit test charge here, it's going to move that way. If I keep a unit test charge here, it's going to move that way. Now, anywhere in here, the unit test charge is going to go away. So, this represents the field lines around a positively charged object. So electric field lines for a negatively charged object, they all converge to the negative charge, and these are the electric field lines for a positively charged object. So electric field lines due to a positive charged object will all diverge from it, and electric field lines due to a negative charge will all converge to the charge. In a region where the field is stronger, the field lines are closer. Look at this, the field is actually stronger near the charge, where the lines are all closer. As you go away, the field becomes weak. It means the lines will all become widely separated. Alright, whereas in a region where the field is weaker, the field lines are farther apart. If two positive charges are situated in a place close to each other, can you visualize? If I now place two positive charges separated by a small distance, like this, well, I have two positive charges now. What will the field lines look like of these two charges? Can you visualize how they're going to look like? Well, they will look like this. In other words, if I place a positive test charge here, it wants to go away from this and also from this. It will go somewhere in that direction. So each of these lines tell you the direction in which a test charge will move. If you place a test charge here, it will move away like that. On the other hand, if I place a test charge here, it will have no force on it. Why? Because this will pull it away that way, this will pull it away that way, and it will have no net force on it. So this is called the electric field lines due to two positive charges. Similarly, we can construct electric field due to two negative charges. How will they look? Look at this. This is a negative charge, this is a negative charge. The field lines will look like this. If you keep a unit positive charge here, it will move over that way. If I keep a unit positive charge here, it will move like that. So there you have the unit, the electric field lines. But look at the electric field lines due to a positive and a negative charge. That's very interesting. If I keep a positive unit charge here, it will move away from the positive charge and towards the negative charge. Look at the paths. Each of this line describes the path that the unit charge will take when placed at any of the points. I want you to take a closer look at it and learn about this. Well, we have actually done a brief description of electric charges, how we can charge an object either positively or negatively, and the concept of electric field. In the next lesson, we will build on it and we will see how electric charges can be made to move to produce an electric current.